So this video is about current electricity. So far we dealt with static electricity. Now we're going to look at current electricity, and here are some of the sources for that. We've got solar panels, we've got generators, we've got windmills, we have batteries, lots of different places we can get a source of electrical power from that is more in a current form as opposed to static electricity. So static electricity, again, it's like that quick zap, that bolt of energy that jumps from one thing to another, like here and up in the Tesla coils you see up in the top there. You get a whole lot of energy, but it's not consistent and it's not regulated very well. So the amount of energy that gets released can change. The timing of that energy is not controlled. It takes a lot of energy to jump through air, so not a great way to charge things, right? We need to be able to control all those things, and that's what current electricity is all about. That's what we're going to plug our iPhones into. That's what we're going to plug our devices into to charge them up, is something that allows for them to receive a controlled amount of electrical energy at a given rate that they can manage to use to run a battery, to charge a battery up, to run your refrigerator, to run the lights in your house. Okay, you can't run those off things that have variability with them. So we need to manage that variability. Otherwise, you might end up with a phone over there on the right where the variability wasn't managed and that Samsung caught on fire while it was charging and burned through the whole thing. So what two types of current do we have? Well, we have direct current and we have alternating current. And see here on the left in direct current that there is a constant flow of electrons through the loop of the circuit from one end of the battery to the other. Okay, so that's key, that electrons and charge are just going to stay going in the same direction the whole time. The other thing here is that the voltage on the system is constant. Now, quick information here, voltage, and we'll get into this a little bit more later, is kind of like the push on electrons or charge to the circuit. And that comes about from difference in charge, right? We saw that with static electricity, Coulomb's law. The difference in charge is going to force electrons somewhere. Well, that's the same thing in a circuit with current, is that we have this push because we are applying what's called a voltage across the system. So from one point to another, there's a difference in charge. That's going to make electrons move. Okay, so a battery gives a set constant voltage to the system. So electrons are going to move at a constant rate. Well, the other type of current is called alternating current, or AC, and that's where the electron flow is going to shift one direction to the other at a given frequency. And the voltage that's applied to that is going to vary. It's going to vary over a positive and negative range. So for direct current, the voltage might be a straight line, whereas in AC, the voltage is going to go like this and just oscillate back and forth, which is going to cause the electrons to move one way and then slow down and move the other way. Both are good ways for giving energy to systems. Again, here we're giving energy to the system, pushing electrons one way, then they're pushing them back the other way. So that energy of that is what the system will use to convert to light, heat, whatever. Whereas in direct current, it's just the energy of pushing these electrons through is what's going to generate some kind of dissipation of that energy through a light or some kind of mechanism. So a couple different things about that. Direct current is typically generated by batteries and solar panels. Again, constant direction flow. It's used by a lot of your modern technology. So computers, battery chargers, LED lights, all of those things use direct current. Because direct current doesn't come from your wall socket, though, your wall socket's actually AC, then you need to have some kind of converter. So that little thing that adapter you plug into the wall, that is going to take that AC current from the wall and turn it into DC. That's why that thing heats up, because you are losing energy when you do that. It takes energy to go from AC to DC. It's not a perfect one-to-one conversion in terms of the amount of electrical energy in there. Plus, it also regulates the amount of energy that kind of passes through. You can't put all of the voltage that's in the normal AC wall socket into a battery in a cell phone. If it did, you'd just fry it. The energy would be too much. So we need to manage that, and that's what we do using those adapters. So alternating current, though, comes from large generators. The great thing with that is, and at least early on, which is why our whole electrical system is set up that way, it was very easy to change voltage. It was easy and cheap to regulate the amount of voltage that was coming across the system, as opposed to DC at the time. It was very difficult to do things like that. It also made it really easy to travel long distances, which is key for a grid because, well, you're not going to have a power generating station everywhere. We have power generating stations in a central location and needs to disperse its way out. The best way to do that was through alternating current, best and cheapest way to do that. So Thomas Edison really pushed for DC, but because of that ease and cheapness for alternating current, for manipulation and travel, the AC current of Nikola Tesla actually won out, and that's why pretty much all electrical grids are set up that way. There are some places that are trying to switch over to a little bit more DC friendly environment because, well, all our things that we use are use DC current now most of the time. So to cut down on that transformation energy loss, okay, that would be a big deal, right? You wouldn't lose as much energy. This grid would be more efficient if you didn't have all of these little things that required an AC to DC converter, and you just converted to DC once. That would make a big difference in terms of saving energy. But that's still a little ways off. They're still debating about a lot of that stuff. It would be a really expensive fix too to just fix the whole system. In the US, our system uses AC at about 120 volts, alternating at 60 hertz. So every 60 hertz, it is cycling through, okay? Whereas Europe uses 250 volts, alternating at about 50 hertz. This is the reason why you need an adapter when you go to other parts of the world. The plugs are different because if you plugged your device straight into a wall socket in Europe, you'd fry it because there's too much energy. It would overload the circuit capacity really quickly and fry your battery or fry your circuit. So you need to take that voltage down to what your device is meant for. Your device from the US is meant for 120. So if you plug it in at 250, that's twice the amount of energy that it normally gets. And it's not designed for that. So that's why you need all those converters when you go to other places. Anyway, so about a couple of those terms that we just mentioned. Voltage is also known as electric potential energy, and it's basically the drive, the push to move on electrons to move from one point to another. So how much charge difference there is from one side to the other. So again, thinking back to Ohms Law, the more positive charge you have somewhere, the more negative, and let's change pens, that's not going to show up here. The more positive charge you have on one side, the more negative charge you have on the other, the more of a push you're going to have for those electrons to go from there to there. Now, in static electricity is all about going through the air. So you need a lot more voltage energy to get through that. But in current electricity, we're going to use a wire to get from one side to the other. That's going to reduce the energy it takes to get through because, well, wires are good conductors. They have a very low what's called resistance, which we'll get into in a second. So voltage is measured in volts, okay, which is going to be with a capital V. So we have volts, which is a capital V, and it's going to use the variable V. That's a key there, okay? So just a couple quick things. Your standard batteries that you guys might use, your AAAs, AA's, C batteries, D batteries, they're all about 1.5 volts each. Again, the household circuit is operating about 120 volts. So just kind of remembering those facts is important when we're kind of dealing with some of the equations in a little bit. Next thing is current. So current is basically how quickly charge is moving through the circuit. So it's a rate of flow. It is measured in amperes or amps. Okay, typically just referred to as amps, capital A, and it uses the variable I. So I, when you see that in an equation, is the current. Okay, it's probably the only really confusing part about this whole thing, is making sure to remember that I represents the current, or the rate of electron flow through the charge movement through the circuit that we're dealing with. Resistance is the last term, and resistance is a measure of how difficult it is for charge to move through said circuit, how difficult it is for electrons to kind of pass through something. It is measured in ohms here, and it uses the symbol omega to represent it. And it uses the variable R in equations. So R is resistance, which is measured in ohms, and you will abbreviate it with omega. Okay. So 3 pretty simple terms, and looking at the mathematical relationships, it all really kind of makes sense. It all comes together in one simple equation, and that's called Ohm's Law. So Ohm's Law very simply is the voltage is equal to the current through a circuit times its resistance, okay? Or the current that flows through the circuit is equal to the voltage applied across that circuit divided by the resistance of that circuit. The second version here is probably a little better in terms of understanding like what it really means. Even though this is kind of V equals I is the way you're going to tend to see it, I equals V over R will define it a little better. Because what that means is the rate of flow of charge or current through the circuit is directly proportional to the voltage. So this means that if V goes up, you look at this equation right here, I equals V over R, I is also going to go up, okay? Which makes sense. If you're pushing on something to get through the circuit faster, it should get through the circuit faster. If there's more drive, there's more push, then you're going to get a stronger current. So you put more batteries or a stronger battery on a circuit, okay, you're going to get more current through it. That's why you don't want to plug your phone into a 250 volt outlet. Your phone's designed for 120. If you put it into 250, all of a sudden you've doubled the voltage. You're going to double the current through trying to flow through that phone, and it's going to catch on fire, or it's going to have some problems. Okay. So there's one relationship there. The current is going to go up as the voltage is going to go up, assuming the resistance stays the same. And the other relationship there is that if the resistance in your circuit goes up, the current in your circuit is going to go down, which completely makes sense. If you are pushing with the same force, same energy on electrons to move through the circuit, but it's harder to get through the circuit, well, the rate of electron flow through your circuit is going to drop. So at this point is a good time to go Actually, let's do one more thing. Talk about power really quickly, and then what I want you guys to do is do the first homework worksheet. So power is the rate at which energy is used, or how quickly the electric potential energy is going to be converted to some other form. Okay, and power is equal to the current times the voltage. Before, we always remember that power was equal to work over time, but we're really actually doing the same thing, because work is a form of energy. Remember, this was an energy, and this is time in seconds, right? Well, I is equal to how fast something's going, so it's 1 over seconds. And V is also the energy. So when you multiply those two things times each other, well, you get energy over seconds. So when you multiply IV together, you're going to get the power, which is the rate of energy use, which again, just like before, is measured in watts. These other two equations, P equals I squared R, V squared over R, are literally the exact same thing, just using the fact that in this case, we plugged in V equals IR into this equation. So we end up with I times IR, so I squared R. And this equation plugged in the fact that I equals V over R. So I'm going to get rid of that first one. And by doing that, you end up with power equals V squared over R. So just an idea of how you're going to find electric power. So talking about power for something, you're talking about how much energy is being used in it. Okay, and kind of the rate at which, not just how much, but how quickly it's being used. Okay, so the next thing we're going to talk about is just thinking about old school light bulbs, okay, but even newer bulbs that would be LED based. Thinking about which one has more resistance, a 60 watt bulb or a 120 watt bulb. You might think, oh, it's a 120 watt bulb, it's got greater resistance, or it's a 60 watt bulb, it's got less resistance, it's a smaller wattage, it's using less energy, but it's actually backwards. Since P, this is important, since P equals V squared over R, and the voltage for both light bulbs, the voltage for both light bulbs would be 120 volts, right? And P would be 120 squared over R. To increase P, we are going to have to decrease R. Okay, so a 120 watt bulb is brighter because it's got a greater current, because the energy of the charge flowing through is the same for both. They're both coming from a 120 volt socket. Okay, they are both getting the same energy. It's going to be who can use it faster will be the one that is brighter and use up more energy overall. So that's why a 120 watt bulb actually has less resistance than a 60 watt bulb. Okay, so hopefully that makes a little bit of sense. So some basic concepts to know here. Objects with more resistance have slower currents, so they use less power. Okay. Objects with greater power usage tend to have less resistance. Household circuits tend to operate 120 volts AC, which a lot of our devices will convert to DC. And there's also an important thing, fuses or circuit breakers. So it's like there's a gray box outside your houses that might have a lot of black switches in it. Okay, that's the circuit breakers. Basically, they control the current for a given circuit. That's why if you're running something in the kitchen, like the mixer, and you plugged in a space heater and you're running a TV, you've got a really old house that's not designed very well or something, and all of a sudden everything shuts off. Well, what's happened is you start to draw too much current, because each one of those is going to add current that's taken out, and that total has to be less than what the fuse will allow. So circuit breakers at your house tend to allow 15 amps to, some of them will go up to like 50 amps for things that require a lot of electricity, but typically it'll be 15 or 25 amps. And that'll be the max amount of current that can go through that one set of plugs in one location. Small devices will have a small little fuse inside them. A lot of times it's a little glass tube that looks like this, has a little wire going across, and as soon as that current gets too high, that thing breaks, and then the thing shuts down and stops working. You need to go replace it. Kind of annoying, but it's a good way to control and keep current from getting too high, because current's the thing that's going to cause problems for you. That's the thing that causes fires. Current causes fires. Voltage does not cause fires. It's the current in response to that voltage that's going to cause a fire. So those circuit breakers are there to keep your house from basically burning down. Now, our last thing we're going to do for this video is how to calculate your power bill. So power bill is a very simple function for determining the cost of using electricity, assuming the rate charge is constant. Now, things are different now all the time in San Diego with use of time of usage things and all sorts of stuff like that, but we're going to simplify it down. We have a single rate of charge. So it's also based around a unit called the kilowatt hour. This is the number of kilowatts of power actually used. So since power is a rate, we actually need to multiply that rate times the number of hours that the energy is being consumed to figure out the total amount of energy actually used by the household. It might sound confusing. It's actually really simple. Basically, total cost is going to be power used in kilowatts times the times used in hours times the rate of charge, which is in dollars per kilowatt hour. So, or cost is equal to P times T times R. Key here, though, of course, is getting the units right. The power needs to be in kilowatts, the time needs to be in hours, and the rate should be given. So, for an example, if a 12 ohm hairdryer runs 2 hours every day for 30 days on a 120 volt household circuit, it costs $25 per, whoops, that should be a kilowatt hour, not each watt hour. Change that to a K. How much does it cost to run that hairdryer for 30 days? Okay, so seems like a complicated question. It's really not. So first off, we have P times T times R, 3 things we need. Okay, so first off, power is equal to I times V. Okay, we have V, but we don't have I. So we could also use V squared over R to get the power. So we would do 120 volts squared over 12 ohms, okay, to get the power that we are consuming. And that power would be 1,200 watts. But we need it to be, for this to work, it needs to be in kilowatts. And 1,200 watts is equal to 1.2 kilowatts. So just like all our other metric units, we can just move the decimal point around and get to our right settings there. The time needs to be in hours. So thing here is we're running this for 30 days. Okay, that's not hours. So we need to turn that to hours. Well, each day for this hair dryer is only 2 hours long. It is not a 24-hour day. It is a 2-hour day. So 30 days times 2 hours a day means we're going to be running it for 60 hours in a month. Okay. And then we would need, and then we were given the rate. So we go up here, we do 1.2 kilowatts times 60 hours times 25 cents per kilowatt hour. So 1.2 times 60 times 0.25 means it's going to cost for 2 months, for 30 days, if we run this hairdryer that much, $18 just for that hairdryer. If we run it for that often, that's the resistance of that hairdryer. So it's a pretty easy way to calculate how much it costs to run everything. And it might not seem like a lot. Oh my gosh, my electric bill is $18 over a course of a month. But remember, this is one item from your house. Now, I'm not saying that your hairdryer really is at 12 ohms. It's probably not, because that's a lot of current that you'd probably be drawing there. Talking about 10 amps of current off your circuit. So probably not going to be exactly that resistance, but a hairdryer does need a lot of current to flow through it to get the heat and get the fan to spin. So most hairdryers are actually pretty low resistance. But just so you can see, that's what the power company is doing when they're billing you for electricity. So hopefully this video helped. This point, do that second PDF, that second worksheet, because then you'll have a good idea of that. Takes you through the whole concept of power and calculating cost for electricity.